Hello viewers, in today's session we are going to discuss another important problem from limits, and in this session we are going to find out the right hand limit of this function when x approaches to 0, and here the function is mod of x minus 3 multiplied with the greatest integer of minus x and divided by greatest integer of 1 plus x plus mod of x. So here we have to find out the right hand limit of this function when x tends to 0. So here we have x is equal to 0, and when we approach towards x is equal to 0 from the right of x is equal to 0, then we reach at a point that is 0 plus h, and this is called the right neighborhood of x is equal to 0, right? So here we have to take x is equal to 0 plus h, and when x approaches to 0, then h tends to 0, and remember this h is infinitesimally very small, and it is a positive quantity which lies between 0 and 1, right? So this h is very small, that is infinitesimally very small. So now let us call this limit as L. So L can now be written in terms of h, that is we have limit h tends to 0, and here we have mod of x minus 3. Now x can be replaced by 0 plus h, that is simply h. So here we have h minus 3, then we have minus h, and here we have greatest integer of 1 plus h, and here we have mod of h. So now we have to simplify this expression when h tends to 0. Now see, here we have mod of h minus 3. Now we have just seen that h is a positive quantity and it lies between 0 and 1. So this quantity, that is h minus 3, must be less than 0, right? And mod of h minus 3 should be equal to a negative of h minus 3 when h minus 3 is less than 0. So here we have used the definition of mod function, that is mod of p is positive p whenever p is greater than 0, mod of p is 0 when p is equal to 0, and mod of p is negative p when p is less than 0. So here this quantity, that is h minus 3, is less than 0 because h is less than 3, right? So mod of h minus 3 is equal to negative of h minus 3 due to this definition, right? And here we have mod of h, and mod of h can be written as positive h because h is positive. So when p is positive, that is greater than 0, mod of p is equal to positive p, right? Okay, and now we have to take care of these two terms, that is greatest integer of minus h and greatest integer of 1 plus h. Now see, h lies between 0 and 1, and if we multiply this inequality throughout by a negative 1, then we'll get 0. Then we have here minus h, and here we have minus 1, and the direction of the inequality get reversed. So we have minus 1, minus h, and 0. So minus h lies between minus 1 and 0. So the greatest integer of minus h should be equal to minus 1 due to the definition of greatest integer function. And here we have greatest integer of 1 plus h. Now see, 1 plus h is slightly greater than 1, but it is less than 2 because h is positive quantity. So when we add h to 1, then 1 plus h is slightly greater than 1, but it is less than 2. So 1 plus h lies between 1 and 2. So the greatest integer of 1 plus h must be equal to 1, right? So now using these expressions over here, the limit L is now given by limit h tends to 0. Mod of h minus 3 is the negative of h minus 3, and then greatest integer of minus h is minus 1, and here greatest integer of 1 plus h is 1, and mod of h is positive h. So now this negative and this negative, when multiplied, it becomes positive. So we have limit h tends to 0, and we have simply h minus 3, and here we have in the denominator 1 plus h. So now we have a rational expression here, and when h approaches to 0, then this limit is simply 0 minus 3 over 1 plus 0. So this is minus 3, and here 1 plus 0 is 1. So we have minus 3. So the value of this limit is equal to negative 3. So now let us consider one more example. So let us consider this limit x tends to 0, 1 plus tan x or divided by 1 plus sin x raised to square root of pi divided by sin x, right? So here if we compare this limit with this one, that is limit x tends to a f1x raised to f2x, then f1x is given by 1 plus tan x divided by 1 plus sin x, and f2x is given by a square root of pi divided by sin x, and here the value of a is equal to 0, right? So we have to find out the value of this limit. So let us call this limit as L, and here let us first find L1, that is limit x tends to a f1x. So we have limit x tends to 0, and for f1x we have 1 plus tan x divided by 1 plus sin x. So now this limit can easily be evaluated, because we can write limit x tends to 0, 1 plus tan x, and here we have limit x tends to 0, and here we have 1 plus sin x. So now we have 1 plus limit x tends to 0. Here we have tan of x, and here we have 1 plus limit x tends to 0, and here we have sin x. Now see, when x tends to 0, then tangent of x also tends to 0, and similar is the case with sin x. When x tends to 0, sin x also tends to 0. So now these two limits are equal to 0. So we have 1 plus 0 over 1 plus 0, that is 1 over 1, that is equal to 1. So the value of the limit L1 is equal to 1. Now let us calculate L2. So we have L2 limit x tends to a f2x, and here we have limit x tends to 0, and f2x is square root of pi over sin x. Now here we can write square root of pi in front of the limit notation, and we have limit x tends to 0, 1 over sin x. Now see, when x tends to 0, then sin x tends to 0, right? So this limit it tends to infinity, that is when x tends to 0, sin x tends to 0. So 1 over sin x, it tends to infinity or not defined, right? So here we have square root of pi, and here this limit is not defined. So we have L2 is tends to infinity, that is L2 is not defined. right? So these two functions f1x and f2x satisfies the condition, that is L1 is equal to 1 and L2 is not defined. So we have just seen that whenever we have a limit of this sort, then L1 is equal to 1 and L2 is not defined, then the value of this limit is given by e raised to a limit x tends to a, and here we have f2x multiplied with f1x minus 1, right? So the value of this limit L can now be written as e raised to limit x tends to 0, and f2x is square root of pi over sine x, and here f1x is given by 1 plus tan x divided by 1 plus sine x, and here we have minus 1. So now we can simplify. Here we can write a square root of pi, and here we have limit x tends to 0, and here we have 1 over sine x, and simplifying this term we have 1 plus tan x minus 1 minus sine x, multiplying this 1 with 1 plus sine x, and here we have 1 plus sine x, and here this one get cancelled, and we have e raised to square root of pi limit x tends to 0, and here we have 1 over sine x. Now we are left with tan x minus sine x divided by 1 plus sine x, right? Okay, so now here we can write tan of x as sin x over cos x. So we can now write e raised to square root of pi limit x tends to 0, and we have sin x over cos x minus sin x, and in the denominator we have sin x, and here we have 1 plus sine x. So now we can cancel this sine x by taking sine x common in the numerator. We have e raised to square root of pi limit x tends to 0, and we are left with 1 over cos x minus 1 divided by 1 plus sine x. So now we can write this limit L as e raised to square root of pi, and we have limit x tends to 0, 1 minus cos x divided by cos x, and here we have 1 plus sine x, right? Okay, now see when x tends to 0, then cosine of x tends to 1, because cos of 0 is equal to 1, and when x tends to 0, sine of x tends to 0, because the sine 0 is equal to 0. So now we can write this limit L as e raised to square root of pi, and see here we have 1 minus 1 minus 1, and because limit x tends to 0, cosine x is 1, and here we have again 1 and 1 plus 0, right? So what we have done here, limit x tends to 0, cos x is 1, here we have 1, so we have 1 minus 1, and limit x tends to 0, cosine x, so this is 1, and limit x tends to 0, sine x is 0. So here we have e raised to square root of pi times 0, because 1 minus 1 is 0. So we have now here e raised to 0, and here in the denominator we have 1 plus 0, that is 1. So 1 times 1 is simply 1. So we have now e raised to 0, that is equal to 1. So the value of this limit L is equal to 1. Hello viewers, in today's session we are going to discuss another important and conceptual problem from limits involving the absolute value function or the modulus function. So here we have to discuss the existence of this limit, that is limit x tends to 0, and here the function is given as mod of x minus 3 minus mod of x plus 3 divided by x, right? So here in order to discuss the existence of this limit, we have to make use of the definition of mod function, right? So if we use the definition of mod function, then we can easily arrive at the right hand limit and the left hand limit of this function when x approaches to 0, right? So here in order to test the existence of this limit, we'll find the right hand limit and the left hand limit, and then we'll draw the conclusion, right? So let us first see the definition of mod function, and then we'll calculate separately the right hand limit and the left hand limit when x tends to 0. So let us first see the definition of mod function, right? So here a mod of p is defined as positive p whenever p is greater than 0 or p is positive, and mod of p is equal to 0 when p is equal to 0, and mod of p is negative p when p is less than 0, right? So viewers, the solution of this limit, it lies in the definition of mod function. So if we correctly apply this definition of mod function to find out the right hand limit and the left hand limit, then we can draw the conclusion. So let us first find out the right hand limit. So for right hand limit, what we will do, see here x tends to 0. So now if we draw the real number line here, and here we have the point x is equal to 0. So when we find out the right hand limit, we approach from the right of x is equal to 0. And when we find out the left hand limit, we approach from the left of x is equal to 0. So when we get or we find the right hand limit, then we move towards x is equal to 0 from the right of x is equal to 0, and we arrived at a point in the neighborhood, that is the right neighborhood of x is equal to 0, and this point may be taken as 0 plus h. And when we approach x is equal to 0 from the left of x is equal to 0, then we reach at a point which is known as the left neighborhood of x is equal to 0, and here this point is 0 minus h. So to get the value of right hand limit, we take x is equal to 0 plus h, and remember this h is infinitesimally very small, and it is a positive quantity, and it lies between 0 and 1. So this quantity h is very small, right? So we can take x is equal to 0 plus h when we find the right hand limit, so that we have simply x is equal to h. And when x tends to 0, then h tends to 0. So here the notation for right hand limit is given by limit, and here we can write x tends to 0, and here we write a positive sign, and here we have f of x. So our function f of x is given by mod of x minus 3 minus mod of x plus 3 divided by x. So now we can transform this limit in terms of h. So we have limit h tends to 0, and here we have x is equal to 0 plus h, or x is equal to h. So we have f of h. So now we can write limit h tends to 0. F of h is obtained by replacing x by h. So we have mod of h minus 3 minus mod of h plus 3, and here we have for x we have h, right? So now we have to take care of these two terms, that is the mod functions. So we'll use this definition. Now see, h minus 3. Now since h lies between 0 and 1 and h is infinitesimally very small, so h minus 3 is going to be less than a 0, right? And h plus 3. Now see, h is a positive quantity and 3 is also a positive quantity. So h plus 3 should be greater than 0. So from the definition of mod function, now we can write from here mod of h minus 3 is equal to a negative of h minus 3, because this quantity, if we take h minus 3 as p, then mod of p is equal to a negative p when p is less than 0. So here h minus 3 is less than 0. So we have mod h minus 3 is equal to minus h plus 3, right? And similarly here we have h plus 3 greater than 0, and we can now write mod of h plus 3 is equal to positive h plus 3, because mod of p is equal to positive p when p is greater than 0. So here h plus 3 is greater than 0. So in this case we have taken p as h plus 3, right? So now this limit takes the form limit h tends to 0, mod of h minus 3 is minus h plus 3. So here we have minus h plus 3, and here mod of h plus 3 is equal to positive h plus 3, which is simply h plus 3. So here we have h plus 3, and in the denominator we have h. So now we can simplify this expression in the numerator. So we have minus h plus 3 minus h minus 3, and here we have h. Now this 3 and this 3 get cancelled, and minus h is minus 2h. So we have now minus 2h over h. Now this h and this h get cancelled, so we have limit h tends to 0 minus 2. Now this quantity is independent of h, so we can omit this limit notation. So we have simply minus 2, right? So the right hand limit of this function when x approaches to 0 is given by minus 2. So here we can write the right hand limit, that is minus 2. So now let us calculate the left hand limit. So the left hand limit, the notation for left hand limit is limit x tends to 0, and here we put a negative sign, and here we have f of x. So when we find the left hand limit, we take x is equal to 0 minus h, and again h is infinitesimally very small, and h lies between 0 and 1, right? So we have x is equal to minus h. So when x approaches to 0, from the left of x is equal to 0, then h tends to 0. So now we can write this limit in terms of h. So we have limit h tends to 0, and here we have f of minus h, because x is equal to 0 minus h, that is x is equal to minus h. So now we can write the value of f of minus h by replacing this x by minus h. So we have mod of minus h minus 3 minus, and here we have minus h plus 3 divided by minus h. Now again we have to take care of these two terms, that is the mod functions. So again we'll make use of this definition of mod function. So let us first see this quantity, that is minus h minus 3. Now see, minus h minus 3 can be written as minus, and here we have h plus 3, right? So this quantity is negative, that is minus h minus h minus 3 is less than 0, right? So we'll make use of this part of the definition. Mod of p is equal to negative p when p is less than 0. So if we take this quantity as p, then we have p less than 0. So mod of minus h minus 3 can be written as negative of p. So p is minus h minus 3. So here we have minus minus plus. So we have minus minus plus. So we have simply h plus 3. And similarly, here we have minus h plus 3, which can be written as 3 minus h. Now see, h lies between 0 and 1. So this difference 3 minus h must be greater than 0. So if we take p as minus h plus 3 or 3 minus h, then p is greater than 0. So now we have to take mod of p is equal to positive p when p is greater than 0. So now in this case, this mod of minus h plus 3 can be written as positive minus h plus 3. So which is simply a minus h plus 3. So now we can write the left hand limit as limit h tends to 0, and mod of minus h minus 3 is simply h plus 3, and here we have the negative sign. Then mod of minus h plus 3 is minus h plus 3, and in the denominator we have minus h. So let us simplify the numerator. So here we have h plus 3, minus and minus plus, and here we have minus 3. So in this case we have minus h in the denominator. So now again this 3 and this 3 get cancelled, right? And we are now left with limit h tends to 0. H plus h is 2h, and here we have minus h. So now this h and this h get cancelled, and we are left with limit h tends to 0, and here we have minus 2, right? And since this expression is independent of h, so we can leave this limit notation. So we have simply minus 2. So we can see that the left hand limit is equal to minus 2. So now we have calculated the right hand limit as minus 2 and the left hand limit as minus 2. So we can easily conclude that the right hand limit and the left hand limit both exist, and both are finite, right? So the right hand limit and the left hand limit both exist and finite, and they are equal to each other, right? So the limit of this function, it exists at when x tends to 0, because if we have a function, say y is equal to f of x, and if we are to find out, or we have to discuss the existence of the limit of this function y is equal to f of x when x approaches to a, then we find the right hand limit, which is given by limit x tends to a positive f of x, and then we find the left hand limit, limit x tends to a negative f of x. And if these two limits exist and they finite and they are equal to each other, then we can claim that the limit of this function when x approaches to a, this limit exists, right? And the value of the limit, this limit is equal to minus 2. So to summarize this discussion, we have seen that the right hand limit and the left hand limit both exist. They are finite and equal to each other, and the common value is minus 2. So we can now claim that the limit of this function is equal to minus 2, and the limit of this function, it exists.